The real eval win is not a pretty score. It's catching the prompt or RAG change that quietly made production worse before users see it. This is the setup you'll be able to run after this, which compares baseline and candidate runs on a query and documents and blocks release when behavior regresses. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Model-driven features drift in tiny ways. A prompt tweak or a retrieval change can nudge answers from correct to misleading. DeepEval is a small Python testing approach that treats prompts, retrieval, and agent outputs like code. It gives you repeatable test cases and metrics so you can catch regressions early. Success looks like a test harness that runs in CI, flags a bad candidate, and keeps users safe without manual spot checks. At a high level, DeepEval compares a baseline run to a candidate run on the same questions and contexts. Imagine one question where the baseline answered correctly and a candidate answer changes format or misses the fact. DeepEval records input, context, expected answer, and actual outputs, and then scores them. The score can be a simple exact match or a retrieval hit check. Strengths: clear, traceable failures. Weaknesses: toy cases need good coverage and thoughtful metrics. We will build a tiny, runnable pipeline that anchors a baseline, adds a second case and a metric, simulates a candidate run, measures retrieval coverage, and then gates a release by thresholds. You do not need deep systems knowledge. The examples are simple and map directly to CI checks. Now, we create the baseline test case. Now, we will define the first test case. This snippet sets up the first DeepEval test case to anchor a tiny, repeatable baseline. It imports LLMTestCase from DeepEval and constructs a case with an input question, an expected answer, the current model's actual answer, and a short context. The variable TC holds this single unit of evaluation, and TCS groups it into a list for future runs. Using LLMTestCase makes each example explicit and comparable across versions, which is essential for regression testing. Keeping the context alongside input and outputs helps later when we verify retrieval behavior. The printed count confirms how many cases are ready, so you know your baseline is initialized. This baseline is tiny by design. Start small so the test stays human readable. Use lucid expected answers that represent the product truth. If you create more cases, the harness becomes more robust against noise. Next, we will add a second case and a simple metric. This example adds a second DeepEval LLM test case and defines a small custom metric by subclassing base metric. The list TCS now contains two cases, one correct answer and one miss, 4 versus 4. The class ExactMatchMetric computes a binary score by comparing the actual output with the expected output after simple normalization. The variable m holds the metric instance, and AVIG aggregates its scores across the test cases to produce a baseline accuracy value. Because base metric lives in DeepEval, you can later mix this with other standard metrics. The printed accuracy quantifies today's baseline quality and sets a reference for future changes. That exact match metric is forgiving when outputs only differ by formatting. If you expect variance, consider normalization rules or a fuzzy threshold. The baseline accuracy becomes your reference point for the next candidate run. Now we will simulate a candidate prompt change and compare results. This code simulates a candidate prompt run by building a new DeepEval LLM test case list called canned with improved answers. The variable canned out holds model outputs for the new prompt, and each LLM test case mirrors inputs and expectations from the baseline, while swapping in candidate responses. Using the previously defined metric M, C-scores collects candidate scores, and cand average computes the candidate's mean accuracy. The variable delta subtracts the earlier baseline average to reveal the lift or drop. If you increase the number of cases, the delta becomes more stable and less sensitive to single items. The printed delta shows how the prompt change affected accuracy. When you see a positive delta, you know the candidate improved measured correctness. A negative delta is your alarm. Remember that small test sets give noisy deltas. Use many cases or aggregate over runs if possible. Next, we will measure whether the retrieval context actually contains the fact. This snippet introduces a retrieval-focused DeepEval metric by defining ContextHitMetric over base metric. The function measure checks whether the expected answer text appears in the provided context for each LLM test case. First, B captures baseline retrieval coverage on the original cases. Then, the candidate's second case context is updated to include a direct fact, and C recomputes coverage for the candidate run. The variable gain reports the mean difference, indicating whether retrieval moved in a helpful direction. Tightening the check to require multiple keywords would reduce false positives while potentially lowering the score. The printed gain quantifies how much your RAG context improved. A context hit metric is lightweight and fast. It does not prove the model used the context correctly, but it catches obvious misses where the source material was absent. For tougher checks, combine context hit with provenance traces or token-level attribution. Finally, we will convert these checks into a release gate. This example turns DeepEval results into a practical release gate that catches regressions. The call evaluate cand m rm records candidate results with both ExactMatchMetric and ContextHitMetric for traceability. Thresholds min-ac and min-rag define acceptable minimums for answer correctness and retrieval support. The variables ACCOK and RAGOK validate those targets, while no reg ensures the candidate did not fall below the baseline delta. You can raise thresholds to be stricter at the cost of more blocked releases, or lower them to allow more changes through. The final printed flag shows whether this build is blocked, making the go-no-go decision explicit before deploy. In a real pipeline, you would run these checks on every pull request or release candidate. Store the test cases and results in a table so you can trend regressions over time. Add logging of failing cases so a reviewer can replay the exact question and context. Recap: DeepEval is a simple Python test harness that records inputs, contexts, expected outputs, and model answers. Use it when you want automatic guardrails for prompts, retrieval, or agents in CI. One caveat is coverage. Small case sets catch obvious breaks, but need careful selection to represent real user queries. Next step, tune the thresholds, min-ac and min-rag, and observe how they trade off blocked releases versus risk in production. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.